have the example. We want to discuss the existence and of the unique solution of the initial value problem. This is my differential equation. So solution of this one, we can find here a2 of x. a2 of x is equal to 3. Then we're having a1 of x. a1 of x is equal to x squared. Then having here a0 of x. a0 of x is equal to 5. And then we're having f of x. f of x is equal to cosine x. Now 3 is a polynomial function. It's continuous on interval r for r real value. X squared is a polynomial function. It's continuous for r real numbers. 5 is a constant, continuous for r real numbers. Cosine of x is continuous. So these are all are continuous on r, that is minus infinity to plus infinity, this interval. Now this is number one, that we discuss the continuity. Number two, we see that a2 of x, that's equal to 3, is not equal to 0 for any x belongs to r. So the second condition is also fulfilled. Number three, that the point x0 must be in the interval r, and this is also true. This is in the interval r. So we say that there exists a unique solution of the given initial value problem. It's very simple. Very simple. We have to check three conditions. Number one, these coefficients are continuous on the interval. Then this coefficient a2 of x, coefficient of y double dash, this must not be 0. This is equal to 3 is not 0 for any value of x in the interval. And number three, this x0 must be in the interval. So x0 is in the interval, 3 is in the interval. So I take another example. In the second example, we want to find an interval about point x equal to 1, for which the initial value problem x square y double dash plus x over this 2 minus x under the root y and 2 over root of x y equal to 0, and y1 is equal to 1, y dash at 1 is equal to 0 has a unique solution. So we are having this coefficient a2 of x is x square, a1 of x is x over root of 2 minus x, a2 of root of x. So we want to discuss the continuity of this one. We know this is a polynomial function, is continuous on the interval r, it's minus 2 to plus infinity. Now when we check this one, the continuity of this one, this continues for r real number, but this continues where 2 minus x is bigger than 0. We take to the other side, minus x is bigger than minus 2, multiply minus, x is less than 2, so it's continuous on the interval minus infinity to 2. X is less than 2, that's minus infinity to 2. So here the last one, a0 of x, 2 is a constant, is continuous for r real number. Root of x, when x is bigger than 0, we say x is bigger than 0. So this interval will be from 0 to infinity, is continuous on the interval from 0 to infinity. This is my interval I1, this is my I2, and this is my I3. We can see here a2 of x, a1 of x, a0 of x are continuous on the interval, I, and I is I1, intersection I2, intersection I3, and this is equal to 0 to 2. So the interval on which they are continuous is from 0 to 2. This is number one. Number two, we want to see this a2 of x must not be 0 at this one. Number two is a2 of x is equal to x squared. And what's my x0? a2 of x, over the interval from 0 to 2. So we're having a2 of x is equal to x squared is not equal to 0 on the interval, open interval, 0 to 2. If it was a closed interval, then it was 0 was in the interval and then it was equal to 0. But it's not inside the interval because open from the left side, so 0 is not there. So it is not equal to 0 on the interval 0 to 2. The second condition is valid. Number three, the third condition is the point x0 we're having here, and that's equal to 1, must be in the interval from 0 to 2. Yes, it is there. So it's also correct. So we say this implies initial value problem will have unique solution. I would like to explain you again these both examples. So we are having here first example. We have this differential equation, and these are our initial conditions. It's my differential equation. This is my initial condition, and this make, when combine them, this gives the initial value problem. So we want to discuss the existence of the unique solution. So when we want to discuss this, we have three conditions. This condition one is that the coefficients, the a0, a1, and a2, a1, a0, and f of x. This is polynomial function, sine, cosine function. Sine, cosine function are continuous on R. So these are continuous on R, continuous on R, continuous on R. Sorry, continuous on R. So these all are, we take the cot of this, their intersection of this, they are continuous on R. Condition 2 was that a2 of x is not 0 in the interval. So we are having a2 of x equal to 3, and then it's 3. So this is not equal to 0 for any value of x. So number 3 was that this a3 is x0 equal to 3 must be in the interval x0 is equal to 3 and must be in the interval. Yes, this is the interval. So we say the initial value problem, there exists a unique solution for the initial value problem. The second question was that we are given here this differential equation. The coefficients are not as simple as in the last equation, and this is my differential equation. And then I was having here the initial conditions, and this make my initial value problem. I want to see it has a unique solution about x equal to 1. So we can just check it. We take a2 of x is equal to x square, a1 of x is x over root of 2 minus x, a0 of x is 2 upon root of x. We discuss the continuity. So this is a polynomial function, it's continuous for r real numbers. So it's my interval I1. So this is continuous for r real numbers, and it's continuous where this is bigger than 0. This one is root is bigger than 0. If equal to 0 is not in the interval. So we say 2 minus x is bigger than 0, x is less than 2. When multiply minus, the inequality is changing. So the third one is 2 upon root of x, and then this must be bigger than 0. This one is bigger than 0, so x is bigger than 0, then we get here interval from 0 to infinity. So we are having now these intervals from minus infinity to plus infinity, minus 2, infinity to 2, 0 to infinity. Then we say a2 of x, a1 of x, a0 are continuous on which interval? Intersection of these three, I1, intersection I2, intersection I3, and this is equal to 0 to 2. Now this is my interval on which these are continuous. Now we check the next condition that this a2 of x is equal to x square must not be equal to 0 in this interval. We check here, we take any value of x here, any value of x is not making it 0. But if there was 0 here, then it becomes 0. But here is open. So x0 is not part of the interval. Then number 3 is that this value where we get the initial condition x equal to 1 must be in the interval. For example, no, x equal to 3, not in the interval, x equal to minus 1, not in the interval. For example, we're having here the conditions like this one, y at minus 1 is equal to 2 and y dash at minus 1 equal to 5. Have the initial value problem a unique solution? No, it doesn't have the unique solution. Are we having here y equal to 5 equal to 2, y dash equal to 5 equal to 0? Have the initial condition, initial value problem unique solution? No, because this is not in the interval. The third condition is not satisfied. But here is 1, and 1 is in the interval. 1 is in this interval. So we say the initial value problem is having a unique solution. We take another example, and we having find interval around x equal to 2 for which the initial value problem will have a unique solution. So again, we take a2 of x, a1 of x, a0 of x, and also here we're having f of x. So we will check all of them. So this is a polynomial function, this is a polynomial function, this is a polynomial function, this is a polynomial function. We say they are continuous. They are continuous on the interval from minus infinity to plus infinity, so real numbers. So this is our condition 1. Our condition 2 is that we check here, number 2, that's a2 of x is equal to x minus 1, x minus 3 must not be equal to 0. What's our interval? This is my 0, this is my 1, this is my 2, this is my 3, this is my -1. When I take the intervals, the intervals are like this one. When the interval from -infinity to plus infinity, so you say from -infinity to here 1, and then we having from 1 to 3. I take this as interval. Then we take this on 1 to 3, then 3 to infinity. Now we say that our number 1, this must not be 0. When you take here the value of x equal to 1, this becomes 0. When you take x equal to 3, this becomes 0. So if we take here this interval from -infinity to 3, the 1 is coming, so it's not possible to take this one. When you take here from 1 to infinity, 3 is coming, so it's not possible. So the interval will be, is not 0 in the interval, in the open interval from 1 to 3. You can see why I take 1 to 3, because I have to check on this one that this must not be equal to 0. Number 3 also help us to make our decisions. This number 3 is that our value of x0 must be in the interval. So what's my value of x0? x0 is equal to 2. Where is my 2? My 2 is not here. My 2 is not here. My 2 is here. So this will tell me that this is x equal to x0 is equal to 2, must be in the interval, and x0 equal to 2 is in the interval 2 to 3. So we say our initial problem will have unique solution on the interval 2 to 3. When I can take as a note, I change my conditions. My condition is y4 is equal to 2 and y-4 is equal to 1. So the interval change. The interval will be now from 3 to infinity. 3 to infinity. So if I take this number 1, number 2, if I take y0 is equal to 1, y-0 is equal to y-0 is equal to 5. Now the interval will change. Now this interval must contain 0. Here it was containing 4. This must contain 0. What's the interval? From -infinity to, it can be from this must contain 0 here. It can be to 1, because we have to check this one also. This must not be 0. If we take it to 3, then 1 comes inside and this becomes 0. No, it's not possible. So we are having this my interval 0. That's here is coming this. Here we have 4 belongs to this interval. My x0 is equal to 4, and here my x0 is equal to 0 belongs to the interval. This here is -infinity to 1. So that's how we can define our intervals for finding the solution, unique solution, that depending upon our a2 of x, the continuity, number 1, number 2, the value x0 which is existing in that one. I just repeat this one again. We are having here the initial problem. This is my differential equation. And these are my initial conditions. Here initial conditions are x0 is equal to 2 at this point. Now we can check here. This is my a2 of x, a1 of x, a0 of x, f of x. They all are continuous because they all are polynomial function on the interval from -0 to plus infinity, number 1. Number 2, we have to check that this value, a2 of x, this is my a2 of x, this must not be 0. This must not be 0 at the point x is equal to 2. Now we take the interval. The interval we just define by this way, that we're having this x equal to 0, this is 0 and x equal to 1, this 0 and x equal to 3. So we have 3 intervals from -infinity to 1, 1 to 2, 3 to infinity. Now we have to check where is my x0 is coming. What's my x0? My x0 is equal to 2 coming in this interval. That was make a correction for the u. This here is 1 to 3. So this was 1 to 3. So it's coming here in this 1 to 2, x equal to 2 is coming here. So we are having here the solution of the has unique solution on the interval 1 to 3. So this here is 1 to 3. We have a unique solution. I change the example. I say the initial conditions I'm having here. This is my initial condition. I change initial condition. They are defined at x equal to 4. Now having the same a2 of x. So I want to take x equal to 4. My x equal to 4 is coming here. This is my x equal to 4. So the interval will be that contain x equal to 4 is from 3 to infinity. I change my initial condition, and I take here the value x0 is equal to 0. So when my x0 is equal to 0 is coming in this interval. So I say here now x equal to 0 is coming here. So the initial problem has a unique solution in this interval when initial conditions are defined at 0. So I've given you different ideas for that one. So this is the how we can find the existence of the solution and existence of the unique solution.